In this video, we're going to be talking about the Jacobian. Now, the Jacobian is used in the general case when we change our variables when we are trying to evaluate integrals. And we've actually used change of variables many times already in calculus. When we changed our variables to polar coordinates or cylindrical coordinates or even spherical coordinates, we were changing our variables from typically x's and y's to something different. And even when we did u substitution was changing our variables from whatever was given to the variable u. For example, this is a typical integral we would have seen in Calc 1. To evaluate this, we know that we would use a u substitution where we would choose u to be equal to x squared. Right? U would be equal to our inside function of the integrand. Then we would have to calculate what is du dx. In this case, well, if u is x squared, du dx is 2x. And then typically the way we would do this in our class, or the way we have been doing this, is then we would try to figure out what do I need to substitute to get rid of that dx, and in this case I also have to get rid of that other x. So how would I get rid of the x dx? Do a tiny bit of algebra, and it turns out 1/2 du is equal to our x dx. So we substitute that in, and now we have a nice, neat integral that we can actually evaluate. But what did I really do? How am I allowed to actually just change variables to make my life easier? And when I changed variables from x's to u's, I ended up with that 1/2 in front. What is that 1/2 doing there? We see algebraically why that is, but what is it really doing there? Because again, when I'm integrating, again, typically a single integral, the idea is that we're doing this as f of x dx. We're summing up our rectangles, where again, f of x would be the height of our rectangles, but dx is that constant width. And so I'm trying to sum up these rectangles of constant width dx, but instead I switch to a different variable u, where now I need to sum up these rectangles that have a constant width of du, but that's not going to be the same. There's going to be something different there, and that's actually kind of where that 1/2 comes in. So you may actually even do u substitution this way, but I want to go back. So when we have that du dx, sometimes the u substitution is actually taught as we isolate dx so that we can substitute it back in and try to cancel. But again, if I go back to this example, my du dx was 2x, a tiny bit of algebra, we can get dx by itself. Dx is going to be 1/2x du. Well, what's really going on is my original rectangles, which had that width dx, if I want to keep that consistent with my new variable, I need to scale du. I need to scale the width of the rectangles in terms of u, and that 1/2x is my scaling factor. All right. Basically, again, that when I change variables, right, when I'm setting up these two separate integrals, one in terms of x and one in terms of u, the dx is the width of my rectangles in terms of x, du is the width of my rectangles in terms of du, there needs to be a scaling factor for me to be able to make that substitution. And that scaling factor is really what the Jacobian is. And this isn't the only place we've seen something like this. When we first started doing our line integrals, and we were trying to parameterize from arc length in terms of s to t, which is how we usually defined our vector curves in space, we had to use the substitution where ds was equal to, and then it's that square root of dx dt squared plus dy dt squared, which is also given as usually r prime of t, its magnitude, and then the dt. Well, that square root right there, that's my scaling factor. That's how I scale between ds's and dt's. That would be my Jacobian in this case. And we've also done it with polar coordinates. That's probably the most common time that we've actually had to do this sort of scaling. So with polar coordinates, our change of variables, we write x in terms of r and theta, and y in terms of r and theta. So we're changing from the variables x and y to the variables r and theta. We're changing our variables here, and so there's going to be some sort of scaling factor when we set up our integral. Now, we've already talked about what this is. We know the answer. We know that when I scale that dA at the end, I have to actually write r dr d theta. I need that extra r in there when I rewrite dA. Now, again, if I kept it in terms of x's and y's, dA is just dx dy, which is a rectangle. But when I switch to polar coordinates, I'm no longer summing rectangles. I am summing sectors. And to do that scale, to switch from summing rectangles to summing sectors, that change in area, that dA, needs to be scaled by r. That r, that extra r, is my scaling factor. Now, to generalize this, our general Jacobian occurs when we are switching from the variables x and y to two new variables, and again, we generalize with u and v. Like we showed with polar coordinates, that was r and theta, but again, to completely generalize, we typically pick our new variables to be u and v, meaning that x is now a new function of u and v, and y is a new function of u and v. And again, we're basically doing a reparameterization from x's and y's to u's and v's. And this parameterization is just like, again, when we did parametric equations before, it's just now our parametric equations are functions of two variables, of those functions u and v. Now, we also need to switch dA in this case too. Again, it's going to have to be scaled. Well, how do I scale that to be in terms of my new variable? Well, essentially what we're going to have to do is find four partial derivatives. And our notation here, dA equals the partials of x and y with respect to u and v. So again, we're going to get a combination of four different partial derivatives, because that's every combination there. And then we can switch to du and dv. And we typically, again, think of this Jacobian as the determinant of a 2x2 matrix, right? So we're going to calculate four partial derivatives. Then we put those four partial derivatives into our matrix and calculate that 2x2 determinant. That 2x2 determinant, that is the Jacobian, that is my scaling factor. That's how I'm going to be able to go back and forth between the variables x and y and u and v when it comes to substituting for dA. Now, just a quick refresher, remember if we're trying to find the determinant of a 2x2 matrix, we're really multiplying the corners and finding their difference. And there's the formula right there. So let's look at the example of polar coordinates again. So when we switch to polar coordinates, we use that substitution that x equals r cosine theta and y equals r sine theta. Again, switching x's and y's into r's and thetas. And so now we have to calculate those four partial derivatives. I actually made you do this on your last exam, and it went really well. So I'm going to kind of fly through this really quickly, but you should really take the time, pause the video, calculate these four partials yourself before moving on. Are you ready? So the partial of x with respect to r is just cosine theta. The partial of x with respect to theta is negative r sine theta. The partial of y with respect to r is sine theta. The partial of y with respect to theta is r cosine theta. Now we want to calculate our determinant. So again, we're going to substitute what we calculated for our partials into this matrix. Then we're going to take the determinant. So again, multiply the corners. So cosine theta times r cosine theta is r cosine theta squared minus negative r sine theta, but negative minus, they're going to cancel out. So plus r sine squared. Well, I see cosine squared and sine squared. We factor out that r, cosine squared plus sine squared is 1, and we get just r. R is our scaling factor, and that's exactly what we knew it was because, well, we've been using it for a while now. But this is formally how we would calculate that scaling factor. So what that means is to substitute dA into our double integral using polar coordinates. dA equals, and again, that first part is really your conceptual idea. What's the partials of x and y with respect to the variables r's and theta, then the dr d theta. And then the actual computational, what you're actually doing, computing that 2x2 determinant, is that right-hand side, right? That whole matrix and finding the determinant, which we said was r, and then of course we have our dr d theta. And that's essentially all we really do when we're calculating these Jacobians. Now, this is also going to come up again as we move into the next section, where we're going to start taking surface integrals. So again, we've integrated over intervals in Calc 1. We've integrated over regions when we did our double integrals. And we even integrated over lines when we did our line integrals. The next step is to integrate surface integrals. And so this is going to come up again as we have to scale our surface integrals. And we'll talk about it a little bit more then.